Here in section 6.7, we're going to be taking a look at word problems where the word problem leads to an equation where variables can show up in denominators. So variables show up in the denominators. We're talking about a rational equation. And here in chapter 6, rational equations are what we learned in 6.6. So the three examples we're going to look at today are going to show you three different categories, roughly in order of difficulty. The simplest type of word problem that leads to a rational equation is something like this, a proportion problem. One of the tricky things about proportion problems, though, is the word proportion may not show up in the paragraph anywhere. You have to know from common sense and your knowledge of the real world that something is proportional to something in the situation that's going on. Here, when you read through the paragraph, we're tagging some rabbits, releasing them, coming back later, we catch 100 rabbits, and 8 of them have tags. The thing that you're meant to think about this is that those 100 rabbits that we've caught, and the 8 that are tagged in that group, that's like a mini little model of what's going on in the whole island. So the idea is that 8 versus 100 ratio, that's supposed to be the same proportion as what you're going to have on the whole island. So here, what you're meant to catch out of this is that the tagged rabbits, that's going to be proportional to the total population. So what that means is when you're setting up your fractions, you're going to want to have tagged in the numerator and total in the denominator, or the other way around. One of those will be numerator, one of those will be denominator, and you can really do it either way. Then you've got to set up two fractions. Anytime you're doing a proportion fraction, or a proportion problem, you'll have fraction equals fraction. And of the rabbits that we caught, 8 were tagged out of a total of 100. That's one of the fractions. The other fraction has to do with this number here, the 45 rabbits that we caught a few weeks ago, tagged. So that's a tagged number. Make sure you put it in the right part of the fraction. And that's all together on the whole island, 45 are tagged. All together on the whole island, what's the population overall? That's our variable. So 8 out of 100, 45 out of the whole population of the entire island, that's the proportionality of what's going on in this problem. Next, you solve that equation. And proportion problems are fairly easy to solve. You cross multiply. In fact, you can start even better, reduce this fraction, cancel 4s, and you'll have an even simpler equation to cross multiply. But sooner or later you cross multiply. X times the 2, 25 times the 45. Let's see, 25 times 45 is 1125. Divide by 2. And you get a fraction, which that doesn't mean that there's like half a rabbit out there. Yuck. I mean, that's kind of gross. But what that means is this is not a perfect process. Those rabbits that you caught last week, they're probably still kind of in the same area, so it's probably not a perfect proportion of the whole island, so you don't expect this to be an exact answer. That's why the question says to the nearest 100. So if you say that there's a grand total of about 600 rabbits, because that answer is closer to 600 than it is to 500, that's a pretty good estimate for the population of rabbits on the island. It's not perfect, but it's pretty good. So, proportion problems, solving the problem is fairly simple because you have this cross-multiplying shortcut. Okay, next type. The next type of problem is called a combining efforts problem. And this is one that's going to lead to a little bit more challenging equation. The idea here is you're talking about two things that are working together. Sometimes they're working against each other, like you might have water that's getting pumped into a pool and then a drain that's draining water out of the pool. And when they're working against each other, you're going to make an obvious change to one of the steps here. But usually they have to do with problems where they're working together and both trying to accomplish something. Here we have two printers, both trying to print out a stack of tests altogether. So there's this new printer that's fast, there's an old printer that's slow, and then there's what happens when they work together. One of those three times we have a precise number for. We know that when they work together, they get the whole job done in 20 minutes. What we don't know is how long each one takes by itself. So read the very first part of the paragraph. My new printer is 3 times as fast as my old printer. So new printer is 3 times as fast as my old printer. It's real tempting to read those words and think it's saying this. But actually put a number in for x. What if the old printer took 1 minute? This is saying the new printer would take 3 times 1 is 3 minutes. And is that faster? That's actually slower. That's the exact reverse of what you want to do. What you actually want to have here is this. The new printer takes 1 minute, the old printer takes 3 minutes. That's faster. That's 3 times as fast as the old printer. So make sure you set up the words and the variables properly. And if you're not sure you've got the variables set up properly, imagine a number in there, and it should make more sense. Now the problem is, you have an instinct that says two things are working together. They're combining their efforts. Your instinct says you should be adding something to something. So it's very tempting to think that x plus 3x equals 20. That doesn't work out right at all. Solve that, you get x is 5, and that doesn't make any sense. How can the new printer take 5 minutes by itself, yet when it's working with the old printer it takes 20 minutes? That doesn't make any sense. So the reason why that's not working is you're looking at the wrong numbers. You will add new plus old equals together. You just shouldn't be looking at the times. What you should be looking at are the rates. Here's what I mean by rates. If it takes 20 minutes to get the whole job done, each minute you get 1/20th of the tests printed. So 1/20th per minute is the combined rate when they're working together. And that's a very easy relationship. You just do a reciprocal. If it takes 20 minutes to get done, it's 1/20th per minute. If it takes x minutes to get done, then it's 1x per minute. If it takes 3x minutes to get done, then it's 1/3x per minute. And here's where your instinct about adding is correct. Those two rates, the new printer's rate plus the old printer's rate, those add up to their combined rate. You can't solve this equation by simple cross-multiplying. You're going to have to do something. Either add the fractions and then cross-multiply, or clear out all the fractions in one go. You have to do something more sophisticated here. I'm going to clear out all the fractions by multiplying by the common denominator. Common denominator here is 60x. Multiply in the first fraction, you get 60. Multiply in the second fraction, you get 20. Multiply in the third fraction, you get 3x. So you end up with a fairly simple equation to solve. But here's one thing to be very careful about. Make sure you read the problem one last time at the end. 80/3 is the wrong answer. That's not what the question wants to know. The question says, how long would it take my old printer? That's 3x. So if x is 80/3, and the answer you're supposed to get is 3 times that, the answer is 80 minutes. The old printer used to take almost an hour and a half to print out all the tests. Now that the new printer is available, it only takes 20 minutes. Okay, one last type of word problem to take a look at, and this is a type that you've studied in the past, distance, rate, and time. By now you should be really familiar with the relationship distance equals rate times time. Another thing that you may have noticed as you worked with distance rate time problems in the past is that there are typically two journeys going on in a distance rate time problem. Maybe two different people are meeting in the middle between two cities, or like in this problem here, the boat goes downstream and then it turns around and comes back. Sometimes the two journeys are the real journey and then the imaginary what if I could have driven faster journey. But there's almost always two journeys. So since there are two journeys and we're talking about distance, rate, and time, a good way to organize your information is with a chart that looks something like this. And in this case, the two journeys were downstream and then back, which would be upstream. And we start filling in the 6 little boxes with as much information as we can find. In this case, we know the distance for sure. It was 24 miles downstream. That was given to us for free. And since the upstream journey is just the same journey in reverse, it's also 24 miles back. Next, we got to talk about the rate. And the rate is not just 10, because there's this current that we're trying to figure out. In fact, that's what the whole question is. How fast is the current? So if you have a current and you're going downstream, whatever your normal speed is, the current speeds you up. Of course, when you turn around and go back upstream, that same current will slow you down. So your rate is not just 10. Downstream, it's 10 plus x. Upstream, it's 10 minus x. And once you have two of the three parts, in this case we have distance and rate, you should always be able to find the third part. If you have distance equals rate times time, that also implies that distance divided by rate gives you time. So here, 24 over 10 plus x, that's how long it took to go downstream. And 24 over 10 minus x, that's the length of time to go upstream. And since it's a total of 5 hours, those two times have to add up to 5 hours. See, the variables are in the denominator. This is a rational equation. To solve a rational equation, you clear out the fractions. In this case, the common denominator is not a particularly sophisticated thing. It's 10 plus x times 10 minus x. So we're going to multiply both sides by that. In this first fraction, when I multiply by 10 plus x, that part will cancel. I'll still have the 10 minus x that didn't cancel with anything. In the second fraction, the 10 minus x cancels, and we still got the 10 plus x that didn't cancel with anything. And then over on the right-hand side of the equation, there's nothing canceling with anything because there's no denominators. So a lot of parentheses, you do a lot of distribution. And then you collect your like terms, which means those 24 x's are going to cancel each other out. But the important thing here is that you're ending up with a quadratic equation. And quadratic equations are a major pain. In this case, it's not so bad because it's a quadratic equation that factors really easily. Factor out the 5 first, and then you have a difference of squares. So you end up with 2 possible answers. Well, wait a sec. Remember, this is supposed to be the speed of the current. And a negative 2 current doesn't make any sense. It's going the wrong way. The water would be flowing uphill. That's crazy. But 2, a 2 mile per hour current, that's a perfectly reasonable answer.